Chris Potter. It is February 3rd, 2017. Got a little presentation for you. Another look at Venus's brightness. A physicist's thoughts. Let's begin, shall we, Booze? Today's song is You Die or I Do. Hans Zimmer, Man of Steel, original motion picture soundtrack action. Put on my other spectacles here. And we will proceed with the power. My last article on Venus's brightness, I used the image shown in figure 1 below and a simple calculation meant to give a rough idea of what the relative size between the moon and Venus should be. Excuse me. In this article, I'm going to do a more accurate calculation. Figure 1, a recent image of Venus and the moon in the sky. Venus seems to be about half the size of the moon, as indicated by the yellow line, with the same length as Venus's diameter in the image. Now we can see from the image above that there's two factors coming into play. Both objects have a different size and different brightness. In other words, the moon looks larger and brighter than Venus. However, I would expect that Venus looks larger, partly at least, due to its unnatural brightness. Let's emphasize unnatural brightness. If we try and compare 2-point objects in the sky, it makes sense to just compare brightness and not be worried about the relative size of the object. But the moon is not a point object, and even Venus looks larger than a point object in figure 1. So the relative size has to be a factor as well as the brightness. Another way of saying this is that a brighter object in the sky will look larger than a dimmer object. So brightness will affect the perceived size of an object in the sky. In my previous calculation, I took into account both factors, size and brightness, as well as the additional reflective ability factor, and came up with the first order approximation, assuming a linear relationship for size and reflective ability, and an inverse linear relationship to do with distance. The equation 1 below, is designed to be an extremely simple it's designed to be extremely simple and provided a minimum estimated value for the relative apparent size of the moon relative to Venus. So, RAPP or RAP M over RAP V is equal to 0.27 over 0.95 times 0.12 over 0.70 times REV over REM, which is equal to 4.9. I want to make sure and read that correctly and accurately. Where RAPPM is the apparent size of the moon, RAPPV is the apparent size of Venus, REV equals 38 million kilometers, or 3.8 times 10 to the 7 kilometers, being the minimum distance between Venus and the Earth, and REM equaling 380,000 kilometers, or 3.8 times 10 to the 5th kilometers, being the distance between the moon and the Earth. The fact that the moon is 27% of the size of the Earth and Venus is 95% of the size of the Earth gives rise to the first factor on the right-hand side of the equation of 1. And the second factor comes from the fact that the moon reflects 12% of the light that falls on it from the sun, and Venus reflects 70% of that light. Let us calculate more accurately each of the factors that play a part in which we see in Figure 1 I will start with brightness. Brightness being that it's given by intensity, and intensity is the power generated by the source per unit area. In this case, the source is the sun. It is the same for both objects, so the brightness or intensity for the moon is given by B moon is equal to P sun over 4 pi, open bracket, RES plus RME, close bracket, squared, which is approximately equal to P sun over 4 pi ES squared. You got that? Okay, great. Where RES is the Earth's orbital radius around the sun and RME is the moon's orbital radius around the Earth. I initially add the two radii. Yeah, that's a cool friggin' word, radii. Because I am going to assume that the moon is full and so on the opposite side of the Earth from the sun. But since the moon's orbital radius is only 0.26% of the Earth's orbital radius, we can leave out the moon's orbital radius from the equation. Excuse me. Then Venus's brightness is given by P Venus is equal to P over 4 pi RVS squared. And so the relative brightness of the moon in relation to Venus is given by B moon over B Venus is equal to P sun over 4 pi RES squared divided by P sun over 4 pi RVS squared, which is equal to RVS over RES all squared. New Venus's orbital radius is RVS, which equals 0.72 AU astronomical units, and the Earth's orbital radius is RES, or 1.0 AU. So equation 4 gives that the relative brightness for the moon with respect to Venus is B moon over B Venus is equal to RVS over RES all squared, which is equal to 0.7 squared, which is equal to 0.52. In other words, the moon has 52% of Venus's brightness. Now the moon reflects a maximum of 12% of the sunlight that falls on it, and Venus a maximum of 70% of that light. Thus, if difference in reflective ability of both objects, if taken into account, we get a new equation for relative brightness. BR moon over BR Venus is equal to 0.12 over 0.70 times RVS over RES all squared, which is equal to 0.089. Now, let us calculate the relative size of both objects. For this, we use angular width. The moon's angular width from an observer on Earth is given by the moon's diameter divided by the distance between the moon and the Earth. A moon is equal to 2 times RM over RME. Pardon me. Where RM is the moon's radius and RME is the distance between the moon and the Earth, and Venus's angular width for an observer on Earth is given by Venus's diameter divided by the distance between Venus and Earth, which is A Venus equal to 2 times RV over RVE, where RV is Venus's radius and RVE is the distance between Venus and the Earth. Hence, the moon's size is in relation to Venus's size is given by the ratio of equation 7 divided by equation 8, which is roughly A moon over A Venus is equal to 2RM over RME divided by 2 over RVE, which is equal to RM over RV times RV over RME. Got that? Okay. Then we know that the moon is 27% the size of the Earth and Venus is 95% of the size of the Earth. We can write RM equals 0.27 RE and RV equals 0.95 RE. Now let us calculate the difference between the Earth and Venus more accurately. Let us use Venus's position for January 24th, which is about 52 days from March 27th, when Venus is at its closest position to Earth. Venus has an orbital period of 225 days, so this is OV equals 83.2 degrees or 1.4 radians of its orbit. Figure 2 illustrates Venus's position on January 24th and on March 27, 2017. Figure 2, illustration of Venus's position on January 24th and on March 27th. The distance, which is the red arc along Venus's orbit between the two positions, is S, lowercase s. All right, so great diagram that's super easy to understand. Venus's position on January 24th, Venus's position on March 27th. Here's the Earth. RVE minimum, RVS, OV, which is equal to 1.45 rads. There's the sun. This is the distance here, isn't it, between those two time positions? Okay. Now all right. So now the distance S, lowercase s, along Venus's orbit can be calculated from the following equation, which is S is equal to RVS times the angle OV, which is equal to 1.08 times 10 to the power of 8 kilometers times 1.45 radians, which is equal to 1.57 times 10 to the power of 8 kilometers. Since Venus's orbital radius is RVS equaling 1.08 times 10 to the 8th kilometers, then we use that result in the Venus's minimum distance to Earth, RVE minimum, which is 3.8 times 10 to the 7th kilometers, to estimate the true distance between Venus and Earth on January 24th, 2017. That formula reads RVE is equal to the square root of S squared plus R min VE squared, which is equal to 1.62 times 10 to the power of 8 kilometers. Using this result in equation 9 gives us equation 12. And that reads A moon over A Venus is equal to RM over RV times RVE over RME, which is equal to 0.727 times RE over 0.95 times RE times 1.62 times 10 to the power of 8 kilometers over 3.8 times 10 to the power of 5 kilometers, which is equal to 121. So the moon will seem to be 121 times larger than Venus. Then if we want to take both brightness and size into account, we need to multiply equations 6 and 12 together to obtain the final equation, number 13. R apparent moon over R apparent Venus is equal BR moon over BR Venus times A moon over A Venus, which is equal to 0.089 times 121, which is equal to 10.8. Gotcha. Thus, the moon is supposed to look about 11 times larger than Venus. Yeah! How did you figure that out, dude? Good job. Then, since the moon only seems to be about twice the size of Venus, in figure 1, we conclude that Venus is much brighter than it should be. The result obtained through the use of this long calculation process is much more accurate, but it doesn't fundamentally change the conclusion at all. The rough estimate was a good enough calculation for that conclusion to be reached, but sometimes a more accurate calculation is needed in order to make the arguments convincing enough. This is fantastic. Chris Potter, Physicist Thoughts. Have a good day and thank you again. Bye now.